Welcome to the Princeton Satellite Systems MATLAB Toolbox tutorials. This is part 2 of the Spacecraft Control Toolbox seminar. In this video, we are going to go through the BuildAgileSat demo step by step. We are going to assume you already have the toolbox installed and your paths set. The first step is to navigate to the demo. We are going to open up the script by typing in edit BuildAgileSat.m in the command window. The script will then open. Now that we have the script up, we can see exactly what this demo does. This particular demo builds a CAD model of a small agile satellite. 2 implementations of this satellite are available here. Variant A has 12 hydrazine thrusters, a radar dish, and a rendezvous camera. Variant B, on the other hand, uses 4 hall thrusters and a telescope. You can look through the specific components on each satellite in the header. Each subsystem is broken down into its various components. Here we have guidance, navigation, and control systems, communication equipment, the payload, the power systems, data processing equipment, the interface, and the structure. The interface is specific to this satellite, which is designed to be deployed by the Space Shuttle's Hitchhiker Ejection Launch System. All of the related and dependent functions are listed at the bottom of the header for your convenience. The first step in actually building the satellite is choosing which variant we wish to use, in this case, variant B. Next, we input the default state data. The radius and velocity are entered in Earth-centered inertial coordinates. We then transform these coordinates into the local vertical, local horizontal frame with the function QLV-LH. We also input the body's rotation in the body frame with the quaternion Q and the angular velocity omega. Next, we set our constants, centimeters to meters and inches to meters, as well as the panel thickness, which is a 1/2 inch. The satellite's core body is now sized, given the maximum dimensions from the Space Shuttle's Hitchhiker Ejection Launch System requirements. Here, all dimensions are converted from inches to meters, as we will later choose the unit for this CAD model to be MKS. We now set the size of the torque rod, as well as its dipole. In the next section, the core's mass data structure is created by inputting the mass, center of mass, and using the inertia's function to compute the inertia matrix. We then size the telescope. We then begin assembling the CAD model using the function BuildCAD The first command to build a new CAD model is initialize. We then set up the spacecraft properties, including its name, the units, and all the properties we defined before for the body. After that, we define the solar arrays. The solar arrays are a predefined structure within the BuildCAD model. All the variables set here are used by that structure. Note that there are 2 solar arrays, one called X and the other Y. BX and BY are the rotation of these solar arrays in relation to the core body. We then size the reflectors as well as the inertial measurement unit, or IMU. As we said earlier, the satellite was designed to be deployed by the Space Shuttle's Hitchhiker Ejection Launch System, or SHELLS interface. The SHELLS interface function outputs predefined parameters of this interface. We also locate the solar array drive. We now begin to specify the different parts of our CAD model. The first part are the bodies. We have 3, the core and the 2 solar arrays. Bodies are made using the create body function, and the main body is always the core. Thus, the core is always known as body 1. All bodies are made with the command make and then are named. For non-core bodies, we must define their rotation from the previous body using B-hinge. R-hinge defines the rotation of the current body in its own body frame, and previous body links it to another pre-existing body. Then bodies are added to the CAD model with BuildAgileSat Model add body. The compute paths command connects all defined bodies. We now begin adding components to each body. Like the create body command, create component also takes the make command, the name of the component, and here, since we have a predefined component such as solar array, we take in panel length, array width, number of panels, all of those variables that we set earlier. For predefined bodies, we can also take other parameters, in this case, electrical conversion efficiency. We also must say which body the component is on. We can also define components such as face color. In the same way we added bodies to our CAD model, we add components using BuildAgileSat Model. Just as we made the solar array front, we define the solar array back, as well as other components on the solar array body, the trusses, the reflectors. Notice that these are made with a general box, and then we give those dimensions in X, Y, and Z. Again, we have rotation in relation to the body, as well as mass. In the same way, we define the second solar array. We now move on to the components which compose the core. Here we have the shells interface, which is made out of a flange, the power interface, and the signal interface. These are made with the generic type, which takes in vertex and face matrices similar to those used in the patch function in MATLAB. We then move on to defining the frame. The frame is defined with panel frame, which creates the honeycomb structure, outputting the vertex and face matrices. Another face is made by rotating the vertices of the first face. We then define the struts using the shaped strut function, which outputs the vertices and faces. This is run through a for loop where we rotate each strut into position and create the component. The side panels are then defined similarly using a for loop. We then move on to defining the cutouts within some of these panels. These are to accommodate the star camera as well as the telescope and the flanges. The panel with cutout function is a special function which outputs vertices and faces that correspond to the cutouts defined. We use another predefined function to create 6 compact PCI chassis. The battery is then defined, as well as the power control unit, since we are using variant B. Likewise, variant B's propulsion is defined as being xenon. The xenon tank is created, along with the tank support and the tank base. Using the telescope dimensions from above, we use the Frstrom function to define the telescope. We now add the star camera. This is a predefined camera using the Astro 5 model, as well as linking to a catalog, the polarstars.txt file. The IMU gets a special structure where we put in the manufacturer as well as the component name. This is just a different way to specify device info. We also add the omnidirectional antenna and the magnetometer. We continue adding sensors such as the high gain antenna, camera, GPS receiver, and the state sensor. We finish by adding the actuators. RWA array creates a reaction wheel assembly array that incorporates the create component command. The array drives are then added, and then the torquers to move the X and Y solar arrays. Finally, we add the thrusters. For variant B, these are hall thrusters. Finally, each set of components is grouped into a subsystem, which is then named and added to the CAD model. This allows for easier access to each subsystem within the GUI. Finally, if one wishes, the CAD model can be exported using the command get CAD model and then exported as either an OBJ or CAD file. You can also create a CAD report in various formats. We now run the function. This may take a minute. We can see its components are added to the model. We can also see the name, units, and number of bodies in the header as well. The CAD Model Viewer GUI is composed of 3 tabs: Component, Body, and Vehicle. The Component tab lets you inspect each individual component's model. We can see the CAD model as well as actual parameters that we defined. Similarly, the Body tab allows you to inspect a given body and look at its physical parameters, including its rotation, mass, and center of mass location. We now go to the Vehicles tab, where we can see the body's state data, as well as a hierarchy of the bodies in each of their components. We can also go to a 2D plan, which shows all of the components from a bird's eye view, as well as the vehicle with all the components assembled. We can click through each of the subsystems to see how they fit together in the structure. Finally, we can show the spacecraft in orbit. This function ties in to our full simulation tools that are available in the Spacecraft Control Toolbox. Thank you for watching this Princeton Satellite Systems MATLAB Toolbox tutorial. To see the next video in the Spacecraft Control Toolbox seminar, or to check out our other tutorials, visit our website at www.psatellite.com.